in this project, we're interested in studying signaling games. So these are going to be situations in which you have a decision maker who's trying to take some action, but what action he takes is going to be shaped by reputation concerns. So if you want, the classic kind of Spence story of students choosing what major, what classes to take, and they care about kind of how the outside market or future employers are going to try to infer something about the student's type from the choices that they make. In kind of classic signaling models, we typically assume that the decision makers' types are kind of ordered by their preferences over actions. That is, the kind of higher types that you want to develop a reputation for being, are those that have kind of lower costs of taking higher actions. So in the education example, it's if you're a smarter student, you have an easier time doing well in more difficult classes, right? And what this often yields is that you can kind of get equilibrium that have full separation. That is, kind of each type takes its own distinct action. And so from one's action, you can basically perfectly infer what type they is. Basically, the equilibrium are kind of perfectly informative about the decision maker's underlying type. And these are often the equilibrium that's under kind of standard refinements that end up being selected. So it's kind of the ones that the literature is often focused on. However, though, in many settings, we think that types are often multidimensional. And this idea that we can kind of order types perfectly by their preferences over these actions is quite a strong one. And that, in real life, the kind of mapping between types and preferences is often a little bit more muddled. So to fix ideas, we're going to be thinking about kind of a setting in which your preferences are going to depend on what we would call a skill type. This is kind of what you care about your reputation for being. So a student, you care about, how employers, what employers think about how smart you are. And the preferences will also depend on a nuisance type. This is something that's kind of not really relevant for your reputation, but is relevant for your choices. Okay. Good. And we're certainly not the first to make this observation. There's a very large literature, including papers by people here. And what this, these settings, the literature is often found, and that we'll find here, in fact, is that having kind of
Andrew, sorry to interrupt, but I can still see just the first title slide. Have you been trying to scroll?
Okay. Oh, wait. Let's see.
It's also not full screen. Maybe that's the issue.
Yeah. Oh, okay. Let me try sharing again. Sorry about that. Let's see. Can you see it?
I see the introduction slide now. Can you try scrolling?
That's where I was.
Yeah, now it's working. Yeah.
Okay, it's working. Cool. Sorry about that.
Try to change slide just because so that we're not. Yeah. Okay. Good.
Cool. Well, all right. So now you can see, I cited a bunch of stuff. All the words I said are there. Good. So where was I? Oh, yeah. So these equilibrium often feature what we would call plausible deniability. That is, if you see a decision maker take a particular action, you're going to get some information about their type, but you're not going to be able to perfectly infer it. So if you think about, an education setting, you see someone get a low test score, you might not know whether that's just because they have a low ability. So, they can't get a high test score, or they might just be somebody who is higher ability, but happens to have really bad test taking skills. Okay. And so this kind of, muddles the situation and makes the equilibrium not perfectly informative. So once we move to this world, where you kind of don't have perfectly informative equilibrium, there's a kind of a bunch of natural questions that come up, in particular, kind of what do equilibrium look like, what outcomes end up being chosen, and how informative are those equilibrium, and how does the informativeness of the equilibrium depend on the setting that we're in. So kind of the, people's preferences and type distributions, and how is that going to impact the equilibrium informativeness. So our goal in this paper is we're going to study a general model of multidimensional signaling. that is, we're going to have kind of both multidimensional types as well as perhaps, potentially multidimensional action spaces under somewhat general preferences, and try to see what we can learn about the structure of equilibrium. So in particular, we're going to provide a characterization of the equilibrium set. We're going to show, even though you have this kind of rich multidimensional space, you end up with some equilibrium that are often quite tractable, possess a very nice structure. And then we're going to explore comparative statics of the model on the informativeness of equilibrium. That is, as we change the parameters of the model, change the signaling environment, how does that make equilibrium more or less informative? Okay. So we're going to develop tools that are going to allow us to explore a host of comparative statics. But the main one, and the only one I'll have time to talk about today, is trying to understand how the spread in preferences impacts equilibrium informativeness. That is, if we make kind of nuisance types more spread out or less spread out, does that make equilibrium more or less informative? Okay, basically, understanding the impact of uncertainty in preferences on equilibrium outcomes. So, off the bat, the answer, to this question wasn't obvious to us, because we kind of had opposing intuitions. That if you kind of spread preferences more, so you kind of take the nuisance types and kind of make them more extreme in some sense, does this make the equilibrium more or less informative? Well, one intuition you might have is that if you have kind of bad skill types and good skill types, as you kind of add more noise to their preferences, this means that there's more bad types that end up looking kind of that have preferences more similar to good types, which makes it harder to distinguish them at the end of the day. And you would think that this leads naturally to less information. On the other hand, though, you would think that, okay, as you make kind of preferences more extreme, this also means that you have types that have more extreme preferences. For them, reputational incentives are kind of relatively less important. And so the actions they choose are kind of more driven by their pure type, and that this leads to more informative equilibrium. So our goal is to kind of parse these two and kind of see whether we can say, do either of these dominate, and can we make, when can we make comparisons on the impact of such changes in the distribution of nuisance types. Okay. And so our main result is going to highlight that these comparative statics are, really depend on kind of whose type we're adding uncertainty to. So we're going to show that equilibrium become more informative if we increase the spread of good types preferences. So that is, means that there's more uncertainty about what the underlying preference of a good skill type is, or if we decrease the spread in bad types preferences. Okay, so we make there be less uncertainty about the bad types preferences. So this is highlighting kind of an important feature of what is it that allows us to sustain informative equilibrium in these multidimensional worlds. Well, it's really having more spread in good type preferences relative to bad type preferences. And I think this is kind of a fundamental point on what is it about a signaling environment that leads to informative equilibria. And if I have time, we apply this to kind of a number of applications where we can use this to think about designers who might change the signaling environment and who want to understand how that would impact the overall informativeness of equilibrium outcomes. Okay, so with that, let me just kind of skip the related literature. I had a couple of slides, but in the interest of time, let me just get straight to the model. So this is going to be kind of a standard signaling game in the sense that we're just going to have one decision maker and a passive observer. This observer is just going to be a belief formation device, so they're not really going to play any active role in the game. All right. Our decision maker is going to take an action x, little x from some set capital X, where capital X is just going to be a convex metric space. Could be one-dimensional, could be multi-dimensional. We're going to allow for both. The decision maker's type is going to be two-dimensional, so it's going to consist of theta and k, where theta is going to be a skill type, which can be either good or bad. So in the kind of education example, I think this is, are you a kind of a high ability or a low ability student, with some prior cue on you being a good type. And it's also going to depend on a nuisance parameter, K. That's just going to be a real number that has a CDF, H of theta. So, just to point out, we're allowing for correlation between theta and K. So this is going to be important and what's to come when we talk about kind of changing the distribution of the nuisance type for bad or good types, that we can hold one fixed and change the distribution for only kind of good types or bad types. Okay. Good. The decision maker is going to have a utility function. Utility is going to depend on three things. It's going to depend on the action that he takes. It's going to depend on his type. And it's going to depend on the observer's belief that he is a good type. So this is the sense in that you only really care about your reputation over being a good type versus a bad type. You don't care about your reputation over your nuisance parameter. Okay. All right, so the utility is going to take the following form. There's going to be this function little u of theta, k, and x. So this depends purely on your type and your action. This is what we're going to call your material payoff. In a couple slides, I'll put a little bit more structure on this, but that's for now, let's just call it little u. And then it's also going to depend on a reputational payoff, rho of nu, where nu is that belief, that the observer's belief that you're a good type. And rho is going to be a parameter that scales up. Basically, how much do you care about your reputation relative to your kind of material payoffs? Okay, good. So we're going to assume that this weight on the reputation is basically large enough to prevent full separation of any type in equilibrium. That is, you're not going to have some types that can kind of perfectly, in equilibrium, perfectly reveal themselves to be good or bad types. Okay. We can give the, we have the exact bound on rho. I'm not putting it up here because it's not super informative, but just know that we can, give you the precise bound. I'll also note that, we're taking payoffs to be linear in that belief nu. That's not super important. Basically, any strictly increasing function of nu will work. We're just going to keep this just for kind of simplicity and, it's what's often done in the literature. Okay. That's it. All right, so timing of the game, the decision maker is going to privately observe their type. The decision maker will then choose an action from the action space. The observer will then see what the action is, form beliefs, payoffs are realized. That's it. So
Can I ask a question here?
Yeah,
Andrew?
Absolutely.
So given that you call these nuisance types, these Ks, my instinct would have been that they would not have entered the decision maker's, the K would not have entered the decision maker's utility function. So the K is purely a noise thing that you have to filter out in some way or so on. But actually here you're making them part of the payoffs. Is that going to be important or not?
Yeah, so we're kind of thinking about this being noisy preferences as opposed to noisy observations of the type. I mean, it is important. It has different implications for kind of what is pinned down by the equilibrium structure. Here, it's more pinned down by the preferences rather than kind of what the noise distribution is. But you're right. That is a different way we could have done things. But yeah, we're treating this as something that is inherent of your preferences, like your access to test prep or something that's going to impact how easily you can kind of do well on a test.
Okay.
Okay. Good. So we're going to study PBE of this game. So this is going to consist of a strategy for the decision maker that's going to map his type into potentially mixed strategies over the action space. And then for the observer, a belief that takes the observed action and then spits out their belief about the decision maker's type. Now, because all that's really payoff relevant is the belief that you're a good type, right? We don't really care about your belief on the observer's belief on your nuisance type. We'll just let R of X denote that equilibrium, the corresponding equilibrium belief that you are the good type, given that belief. Okay. Good. Now, in general, it's kind of, we all know that signaling games often possess kind of a wide variety of equilibrium because PBE kind of tells us what thing, gives us some semblance of structure kind of for on-path actions, but it doesn't tell us anything about what off-path actions could be. And so, you can construct all sorts of kind of somewhat unintuitive equilibria by threatening to punish decision makers via, off-path actions that place really high belief that you must be a bad type. Okay. So in order to kind of get rid of a lot of these unintuitive equilibrium, which we don't really find that plausible, we're going to focus on PBE that satisfy the D1 criterion. So this is the kind of, I'd say the most common refinement that is often used in signaling games. And if you don't remember what it is, kind of roughly speaking, basically D1 tells us, places some structure on if I observe an off-path action, what belief can I hold? And what D1 says is that if I see an off-path action, I have to place beliefs on the types that would have the strongest incentive to deviate to that relative to their equilibrium payoff. Okay. So in our setting, this is basically the type who, for the lowest, observer belief, would be willing to deviate to that action relative to their equilibrium payoff. Okay. So it takes the following form here. So whenever I talk about equilibrium, I'm always going to assume that we're applying D1 here. Okay. Now I'm going to put a little bit more structure on the material payoffs. Okay. So I'm going to assume that there exist these functions V and M such that that material payoff takes the following form. V of theta x, so this is like a skill dependence cost or benefit of taking the action, plus K times M of x. So the interpretation here is that M of x is some common physical cost of taking the action. That's going to be scaled up and down by your nuisance type. And then V theta is kind of the purely skill dependence bit. Okay. Good. Couple of comments on this, kind of the role of this particular functional form. Off the face of it, it looks like we're really imposing a lot of separability between the theta component of your utility and the nuisance parameter component. I'll just note that that separability is a little bit misleading on the face of it because we are allowing K to be correlated with theta. Okay, so this version of the material payoffs is going to be equivalent to one where you have, again, that skill dependent type, but you have some function f of theta comma K times M of x. Okay. Because we can just basically redefine the nuisance parameter as the realization of this f of theta K, and then that's now just the new realized nuisance parameter. Okay. So that's not kind of a super substantial assumption here. Second, the fact that we're taking this kind of multiplicative form is not going to be too important for our results. Really, what we need is that there's some form of supermodularity here. But we're going to keep this form just because it's I think quite natural and tractable. But it's also, when we talk about changes in the dispersion of K, this is going to give us a real meaning to what we mean. If it's going to basically say that when I talk about changing the dispersion of K, I'm basically talking about changing that kind of marginal cost of increasing M of x for the decision maker. Okay.
Yeah, Andrew, going off that, you mentioned this kind of reparameterization in terms of F, but yeah, it does seem like that's going to change the meaning of dispersion in K. So when you say it's without loss, it's not so clear to me exactly what that means.
Yeah, so we'd have to change what the comparative, the nature of the comparative static. It wouldn't be about dispersion of K. It'd be a dispersion of a change in the K that's going to increase the dispersion of this F function.
I see.
So,
got it.
Kind of similar with the supermodularity. Yeah, that's a good point. But yeah. All right. Any other questions? Okay. Good.
Question about K.
Yeah.
K is a part of your type, so it is a multidimensional type, no? So
yes.
K times that, but it is not. Let's say it is not uncertainty on the sender's preferences or something like that.
So K is an uncertain to the observer, but it's so the observer does not know K. The observer knows nothing except the distribution of theta and K. Okay.
I can see.
So and that's going to be important because Otherwise, we'd kind of be collapsing back down to a one-dimensional world. If you could see K, if the observer could see K, and then we're just back to like a one-dimensional signal.
It is that you are going to talk about the dispersion of K later, no? Instead of the dispersion of theta. Yeah?
Yeah, so here we have a binary theta type, and we're not really placing any structure. We could, our comparative, we're going to develop tools in our comparative aesthetics that would allow us to talk about changing these v theta functions, which is essentially changing, the theta in some way. I don't have anything in the slides on that because we're kind of mainly focused on the K dispersion, but yeah, we could explore that as well too. I think that's good. A natural question.
Andrew, one question.
Yeah.
What example should we have in mind to remember this particular functional form? Because to me, the way you were describing the K, I thought it is kind of the marginal cost of, say, effort. But then, it seems that this is actually what the observer may be interested about. So what example should I have in mind to remember this utility function?
Maybe I'm going to give an example in like 2 slides. Maybe let's come back to that then. I think that might help. But
Andrew, I would also guess that you could allow there to be some reputational weight on the K thing, and everything should be continuous. Is that true? So even if the sender cares slightly that people with more access to test prep maybe are better work people, I would assume that should be fine, right?
That would be my intuition. Everything should be continuous, and as long as the kind of relative weight on that reputation is low, I would agree. I should highlight, when we talk about informative equilibrium, we're going to be informative about the skill type, because that's kind of the type that we think the market really cares about. So conditional on holding that fixed, I would have the same intuition. Yeah, good point. Okay, cool. So now let me get to the kind of defining an important object, and I'm going to place a couple of assumptions on this. So I'm going to define what I call the maximized signaling value at some little m. It's called delta of m. That basically says, let's look at all the values of x for which m of x takes the value little m. So kind of along the subspace where we're holding fixed the value of m of x. And then let's pick the action that's going to maximize the payoff, the skill-dependent payoff difference. Okay, the thing that's going to distinguish their material costs the most, holding fixed m. Okay. So I'm going to place 3 assumptions on this, 2 of which are kind of like technical, ease of exposition assumptions. One which is slightly more substantial, but I'll try to argue is we think is kind of a very natural assumption to make. Okay. So first, I'm going to assume that this is a max. Something achieves the maximizer here, and that the action that achieves that max is unique. I'm also going to assume that this is twice continuously differentiable. But then more importantly, we're going to assume that this delta function is strictly concave in M. Okay. And so this last one is, I think, the kind of more economically substantial assumption to make. Okay. However, we're going to argue that basically delta M being concave is kind of a natural property in many settings that arises from the kind of maximization problem inherent in the definition of delta of M. Okay. And that we can kind of generate this strict concavity in many examples where we're not kind of building in concavity into the underlying material preferences. Okay. So to give an example of this, and try to argue that this seems to be kind of a reasonable assumption to make, and to give an example to have in the back of our mind, let's think about a setting which we're going to call kind of multi-dimensional spence. Okay. So we have a student that is choosing how to allocate time across a variety of activities. We're going to index these activities by I in 0, 1. Okay. And for each activity, you can spend up to 1 unit of time on that activity. Okay. So here, what is an action? An action is just basically a mapping from 0, 1 to 0, 1. Okay. We'll assume that the time spent on activity I gives you some learning benefit that at a rate v theta of I. So this is, like if I'm a higher ability, I get kind of more benefit from learning, say about, putting more time into learning on activity I. Or, it could be the opposite, it could be that, bad types benefit more. We're not taking a stand. Okay. But at the same time, you have an opportunity cost of time. And this is kind of our nuisance parameter K. Okay. And so here, your material payoffs are going to take the following form. You're going to kind of integrate over all activities, the total learning benefits. So that's this v theta of I over times x of I integrated over I. That gives us our v theta of x plus k times the total amount of time that you spent. So that's our m of x. Okay. And so, this is kind of an example where we think it's kind of natural to think you care more about the theta than just someone's perhaps just opportunity cost of time in school. Okay. All right. So everything's nice and linear here. Why would I say that kind of strict concavity is a natural property? Well, let's think about what that activity is that is going to maximize the payoff difference holding it fixed m. So that's going to generate our delta of m. Well, this is a constrained optimization problem. It's in fact a really easy one. You just order these activities by their signaling value, which is Vg of I minus Vb of I. How much do they distinguish the good versus the bad type? And then you're just going to fully allocate time across the m activities that have the highest signaling value. All right, you're just going to concentrate all that kind of budget of time that you have to spend on those activities that give you the most bang for your buck. Okay. So let's think about what delta prime of m then is. If I kind of force you to spend a little bit more time on some activity, what are you going to do? Well, you're just going to spend time on that marginal activity, kind of the activity that was, kind of the mth highest in our ranking. Okay. But as we kind of use more and more m, we're moving down the ranking towards things that have lower and lower marginal signaling, lower and lower signaling value. So that delta prime of m is going to decrease as I increase m. In other words, delta is going to be concave. So the idea here is that, if you have this kind of budget of m, you're going to kind of start off by allocating it to things that kind of separate the good types from the bad types the most. But then as you kind of, increase m, you move towards things that have less and less benefit of this kind of skill-dependent type differentiation. Okay, and this naturally generates some concavity. Okay.
Andrew, can I ask one question about this delta? It seems like this is going to play a big role in your analysis. I guess one thing that's puzzling to me, it seems like this maximum could be achieved at some x that's really undesirable for both types. And in that case, it seems like it wouldn't really be relevant. So is there going to be some later assumption that ensures that this maximizer is like a reasonable choice?
So this is kind of built into our kind of assumption that rho is high enough that we're going to basically show you that you're always going to have an incentive to want to deviate towards that activity if it gets you a high enough reputation, and that's going to push towards types taking a high reputation. So maybe it'll be clear when I get to the equilibrium characterization exactly why that's going to play a role, and you'll see kind of where we're using the high rho assumption there. So I think it might be a little bit easier.
I'll also try to answer Ian's question. Isn't that he's correct, right? Like in Spence, we do a ton of education, and that's bad for all of us, and it's bad, and that's the highest signaling value. So in some sense, in standard models, we expect that the place where there's a lot of signaling value gives bad outcomes to everyone. I think that's the expected.
Yeah, absolutely. These could be wasteful signaling in some sense. I think I interpreted the question as, maybe this is so beyond the pale that no one would ever want to take it. And that's where kind of our high rho assumption is going to rescue us. That, basically nothing is too extreme that for a high enough reputation, you wouldn't want to.
Can I ask so here essentially you rank these m's according to their so why wouldn't you just go with the highest? I mean, I haven't seen, maybe it's the K component that I haven't seen, or maybe it's the reputational component that does the work, right? Because if you just choose one activity, then the signaling value is not so great for reputation. I don't know. Is that what this is going to go towards? That you want to choose multiple activities because people it's like picking a sample and choosing the thing that, choosing the max, and that's okay. You chose the max. I want to see the average. Is that kind of that effect, or I mean, I don't know.
So we're going to see this kind of, the fact that you have K this kind of dispersion of K, means that we can't all kind of clump on one action, kind of the thing that would maximize the signaling value the most, because if I see you take some lower action, I have to think, well, it could just be that you're a high type, a good type that had a really extreme K realization. And so, that kind of prevents me from putting really negative beliefs on those actions, and kind of is what's going to create some, what we call plausible deniability, that, I see you take that lower action. Can I believe for sure that you're a bad type? Well, maybe not, because maybe the good type have, for some extreme realization, okay, would actually be the one that wants to deviate to that. And so that's going to generate this kind of spread in the equilibrium actions.
Okay.
Yeah, good question.
Mm-hmm.
Cool. Good.
Just a clarification
yeah.
question. So is K uncorrelated with theta?
It could be, but we're allowing for correlation, and we're going to exploit the correlation later. So because we're going to talk about changing the distribution of K for good types alone, holding fixed the distribution for bad types, or vice versa.
Okay, this is because when you show me the example about this Pence model, it seems to me that K is more or less the same as theta, because it is the opportunity cost of studying. It is more or less your ability is highly correlated with that. No? So in the end, it is the same as having one type.
Well, so you could, not exactly, because again, your type will depend on the distribution. So if I try to infer like you're a joint of theta plus K or something, conditional on that realization, that's going to imply information about your theta type as well as, actually you don't even need correlation for that. So there is going to still be some, the theta is going to be kind of important for understanding what your kind of marginal cost of the action is.
Okay, thank you.
Yeah. Okay, so kind of in a picture, basically what it shows us, this is like the feasible set of M and that kind of skill-based differentiation you can achieve. Delta M basically corresponds to this kind of frontier. For each value of M, what's the largest signaling value you can get? And here we've drawn it concave because that's going to be our assumption. Okay. Now we're going to identify points on this frontier. They're obviously going to be important given how much time I'm spending on them. You can identify them by kind of the point M that they correspond to, but it's going to be useful often to talk about them and basically parameterize it according to the slope of the frontier at that point. Okay, so I'm going to talk about X superscript delta as basically the action that generates this frontier at the point where the slope of the frontier is equal to delta. Okay, this is just kind of a norm, reparameterizing how we talk about the frontier. Okay. So it's just a bit of notation. Okay, so we have a bunch of other examples, besides this kind of multi-dimensional Spence. This kind of action space allows us to generate a rich set of examples, with kind of, things about information choice or mechanism design. I'll just say that, if you want, we could also fit kind of a standard one-dimensional framework in this, in our model. We're not kind of reliant on X. Nothing is going to be reliant on X being in large dimensional, a large dimensional space. Good. Couple of discussion points. The fact that we have identical weights on the reputation for both types, that's just a normalization. For our equilibrium characterization, we can actually provide a characterization even when dropping concavity. Okay, so concavity is going to just be more important for our comparative statics results. We have some work in progress on trying to extend the comparative statics, for general delta, but that's still work in progress. We also have some work on, we can extend some of the characterization results to non-binary theta when we put a little bit more structure on this v theta of X. And we're still working on trying to extend comparative statics to that case as well. Okay, so in the remaining time, what I'll do is I'll go through the equilibrium characterization, talk about what actions are taken, who takes each action, and then we'll talk about the comparative statics, where we're going to talk about changing the distribution of K for various skills types according to the dispersive order. And we're going to compare I could do kind of like a weak set order comparison on the Blackwell informativeness of the equilibrium. Okay. With that, let me get into the equilibrium characterization. So one little bit of shorthand, I'm going to let little g denote kind of a good type who has nuisance parameter little g, and little b denote a bad type who has nuisance parameter little b. Okay. So our first theorem is going to provide an equilibrium characterization. You can see this is a very big box. So there's going to be a lot here, but I'm going to kind of highlight exactly the kind of qualitative things I want you to take away from it. Okay. So we can show that basically a strategy for the decision maker sigma and a belief nu for the observer is going to be an equilibrium if and only if there exists these two cutoffs b0 and b1, and a differentiable and strictly increasing function phi that's basically going to pair bad types between b0 and b1 with good types such that the decision maker takes the following action. So let's focus on the bad type for now and kind of focus on this middle case for b that are between b0 and b1. They are going to take the action x superscript b minus 5b. So this is the point on the frontier that has the slope b minus 5b. Okay, so this is already telling us that kind of everything that you're going to take are those points that generate that maximal signaling frontier. Okay, and if you're below b0, then you just kind of pool with the b0 types. If you're above b1, you pool with the b1 types. Okay? And this phi function is a pairing in the sense that the good type that is mapped to for a particular bad type, so phi of b, is going to take the same action as that b type. So these are basically, this function is just pairing types that choose the same action. Okay, good. We're also going to require that b minus phi of b is decreasing in b. Okay, so this is saying that the slope at that point on the frontier that a type b is choosing is decreasing in b, which just means that they're choosing a higher m. So basically, this is just monotonicity, that if you have a higher k value, you end up choosing a higher m. Okay, but it's gonna be important for what some of the intuition of what's to come. Okay. Next, we show that basically you have to have a kind of an envelope characterization of utilities for each type. We can place some bounds on where these b naughts and five b naughts have to lie, b1, 5 b1. And then, we need to make sure that this nu satisfies Bayes' rule and is consistent with D1.
I'm a little confused about the notation. So x b minus 5b, that's like raised to the power or like just indexed by it?
Sorry, that's superscript. It's not raised to the power. So this is, remember, x superscript delta is the point on the frontier where the slope is equal to delta. So this is the point on the frontier that slope is equal to b minus 5b.
And Andrew, is the claim that if the first 4 points are satisfied, there exists a nu that satisfies 5?
Is that the case? I don't think that's the case. I think you still need that. We need the nu is pinned down. Like the reputation function has to basically correspond to the phi function that we choose.
But I'm saying, does it always exist? I mean, could I choose? Might there be some phi functions that satisfy the first 4, but then there's no nu that can be defined consistent with this, or?
That's a good question. I'm not entirely sure.
Okay.
We're going to construct the equilibrium, but yeah, that's something we could definitely think about. Okay, cool. So the main two things I want to take away from the theorem are kind of what actions are chosen. It's actions on the frontier. Who chooses what actions? Basically, that's pinned down by that phi function. This mapping that maps goods and bad types who take the same action. Once you have that mapping, you can actually tell exactly what action they're going to choose. So the mapping is really the key equilibrium object, as well as these kind of bounds b0, b1. Okay. We can also give conditions for equilibrium uniqueness, and kind of where within type pooling occurs. It could be that B minus 5B is constant across some span of B, so you have a set of all types that are all taking the same action. But I'm not. We don't have time to go into that. We can also kind of extend the characterization to the case of arbitrary delta with some modifications. Okay. All right. So visually, basically the equilibrium set just corresponds to an interval along this frontier. Okay. The fact that phi was continuous means that this B minus phi B is going to be continuous, and so we have an interval. There's no holes in the middle. Okay. So this is kind of nice because it basically says, well, you can think of everything as kind of along a one-dimensional interval along this frontier. It's going to basically simplify the analysis of the equilibrium quite a bit. Okay. All right. Let me quickly give a little bit of intuition for why you want to kind of only have actions on this frontier. Let's suppose that you had some equilibrium and you're choosing some action x tilde. Okay. And there's some B type, B tilde, and G tilde that are choosing this action. Okay. And we want to think about a deviation to choosing x of m tilde, basically the point on the frontier that has the same value of m as x tilde does. Okay. Well, first we have to think kind of, let's suppose that this is off path. Okay. And we want to think about who would have the highest incentive to want to deviate to this action. Okay. Well, for each B type, you can show that basically the B tilde type is going to be the type that has the highest incentive to deviate. And for each G type, the G tilde type is going to be the one that has the highest incentive to deviate. So really, we just have to compare the incentives to deviate, but for B tilde and G tilde to this x of m tilde. Okay. But because we're holding fixed, that the comparison the m tilde, the change in kind of the deviation value for these two types really just hinges on this skill-dependent point. And the fact that x of m tilde is on the frontier means that the difference in the skill-dependent bit is higher at x of m tilde than it is at x tilde. Basically, this is saying that a G tilde type has the strongest incentive to want to deviate to that frontier. Okay, so this is where we're going to apply D1, because D1 is going to say that you have to believe that it's a good type that wants to deviate to this point, because they strictly have the strongest incentive to want to deviate. But this would imply that the reputation is 1, and this is going to contradict our high rho assumption that we can't have separation on the equilibrium path. So this, to get Ian getting to your earlier question, this is the kind of point at which we're using. Okay, so that tells us that basically everything has to lie on the frontier. Now, how do we know that you can't kind of skip over anything in the middle? Well, what we do is kind of a similar argument. We basically show that, if you did have some skipping point, then you could kind of construct a line connecting the kind of endpoints of those points being used, x of m1 and x of m2, and then find a point in the middle that's on the frontier and basically show that that again would have a reputation of 1. So, in the interest of time, I'm just going to kind of skip over this because I want to get to the comparative statics. Okay. Oh yeah, and then quickly, I want to note kind of why does this take the form x superscript b minus 5b? Well, this basically follows from the first order condition in equilibrium that says if you're choosing some value of m and you're a k type, the derivative of choosing a slightly higher or lower m has to the first order condition at that value of m has to equal 0. Okay. And so, that has to hold for the good type choosing m and the bad type choosing m. So the bad type choosing m is going to be b. The good type choosing m is going to be, say, 5b. That reputational payoff's the same. So when you kind of equate those two, that's going to cancel out. You kind of rearrange things a little bit. And what you get is that b minus 5b has to equal delta prime of m. Okay, which is just basically pins down that action that they choose, the m, has to be generating a delta prime equal to b minus 5b. Okay. Good. Now, this is where kind of our monotonicity requirement comes in, and concavity is going to play a role, which is that if higher b have to choose higher m. And if you look, that delta prime is going to be decreasing. So if you have increased b, the left-hand side has to go down, which means the right-hand side has to go down as well, which means that phi prime has to be greater than or equal to 1. Okay. Intuitively, this is saying that as you move through the B types, the kind of set of G types that you're moving through kind of has to be going, you basically have to be moving through the G types at a faster rate, right? That's what this phi prime equals 1, which means that, if you have some span of B types choosing different actions, the set of G types that are going to be choosing those actions has to be greater than that. And so this is already pointing to this idea that you're going to need greater spread in the G types rather than the B types to sustain this equilibrium. And so it's kind of hopefully highlighting some idea that we need spread in good types in order to have informative equilibrium. Okay, so with that, let me get into the comparative statics. Okay. Good. So in order to have informative equilibrium, we're going to need a range of actions being chosen. Like if everybody chose the same action, we're all pooling, there's no information. Okay. What is that range of equilibrium actions being chosen? It's basically the set of x of delta, where delta lies between b1 minus 5b1 and b naught minus 5b naught. Okay. So this span of actions is going to increase if either b naught increases or b1 decreases. That is, the span of bad types that are choosing different actions kind of compresses. Or if 5b naught decreases and 5b1 increases. That is, the set of good types choosing different actions increases. It's kind of like a spread of the good types, or a compression of the bad types. Okay. This basic intuition, the kind of looking at kind of how that span changes, actually allows us to derive some comparisons for extreme cases. So we're going to kind of look at what happens as we take the good type distribution and compress it down to being a single point, or similarly for the bad type. Okay. So I'm going to state some comparative results. These are kind of stated somewhat informally, but all the definitions are exactly what you would expect them to be. So let's take the good type distribution of K and compress it, look at it as it converges to kind of a single point, kind of the Dirac measure on some G tilde. Okay. Then what we can show is that basically all equilibrium converge to being uninformative. That is, if you have no uncertainty about good type preferences, it's not possible to have informative equilibrium. Okay. However, if you do the same thing with the bad type preferences, then all equilibrium are bounded away from uninformative. Okay, so even if there's only one bad type, but as long as there's multiple good types, you still have informative equilibrium. Okay. We can also look at the other extreme, and what we can show is that if you make bad types dispersed enough, then in fact all equilibrium are exactly uninformative. That is, you can't have any information, everything just pools on a single point. So that's like the B1 and the B naught are identical. Okay. We can also show that if Hg, though, gets sufficiently dispersed, then all equilibrium are bounded away from being uninformative. So large dispersion, large uncertainty about good type preferences does lead to informative equilibrium. Okay. Good.
Andrew,
so,
can I ask for some clarification on this? So I might be missing something, but the point here is that you have a range of actions, right? And then, but these actions are chosen by different types, and so it's the distribution of the distribution over the probability of taking a particular action that, in a way, I really care about, not how wide this is. So I'm really confused to the point that I don't understand where the theorem you just explained kind of deals with that. Because at first it looked like, what does it mean to make it bigger or smaller? But if you could just clarify that again.
So I think you're getting to my exact next point, which is that just talking about increasing or decreasing the span is not really related to the informativeness of equilibrium at all, right? What I was being kind of hand wavy and saying is that if I collapse the interval to being a single point, then I know it's uninformative. And if I have a span of actions, a non-degenerate span of actions being chosen, I know that it's not uninformative. And so this is all just basically comparing those, degenerate span to some span, but you're absolutely right. I can't just look at the span of actions and say infer anything. And that's exactly what I'm going to say next, which is that we want to develop kind of more comprehensive comparative statics. And this kind of hand-wavy intuition about like looking at the span of actions isn't gonna give us anything. So we face a number of issues. First, these kind of these B naughts and B1s and these phis that I'm choosing. These are all endogenous equilibrium objects. The variety of theta prime being chosen is only equates to informativeness in the limit if we have none versus some. But if you have increased the span, you could have a Blackwell less informative equilibria. We don't know. In general, we have multiple equilibrium, and they're not going to be ranked by informativeness. We're talking about Blackwell informativeness. It's an incomplete order, so we're going to have a lot of equilibrium that can't be ranked. And so we're going to have to do a lot of equilibrium comparisons if we want to talk about comparing the equilibria set. And in general, we just run into the issue that Blackwell comparisons are difficult. So to make some progress, we're going to place a couple more assumptions, structure on the model. Okay? So the first we're going to make is that we're going to focus on what we call costly signaling environments. That is that as you move along the frontier, the material payoffs for at least one type are kind of monotonic. So here, let's just assume for the bad type that their material payoffs as you increase M go down. This is kind of, most signaling games that we study, we kind of already implicitly are in these kind of costly signaling environments. We haven't imposed any of that before. Now we're going to impose it. Okay. Next, we're going to impose a little bit of structure on the HG and the kind of the densities of the nuisance parameter for these various types. So I have to define a couple of things first. So we're going to say that an environment has quasi-convex likelihood ratios if the ratio of Hg of B minus delta over Hb is quasi-convex in B, and we'll say that it has quasi-concave likelihood ratios if the opposite holds. Intuitively, this is basically kind of a measure of, is there more good spread in the good type preferences or the bad type preferences? If you have a lot of spread in the good type preferences, then Hg is going to be higher on the kind of the extremes, lower in the middle, and so you're going to get something that looks quasi-convex. If Hb, on the other hand, is has more spread in the distribution, then you're going to tend to end up with quasi-concave likelihood ratios. Most standard distributions that we use, normals, exponential, beta distributions, fall into one of these two classes. So we're going to kind of assume that one of these two holds, or well, actually, I haven't introduced the assumption yet, but yeah, so this is kind of a picture of, for a normal distribution, where you have the G types being more spread than the B types, you end up with a quasi-convex likelihood ratio, something that looks like this. Okay, so the two classes of environments we're going to consider are, one, environments that have more G spread. We have this quasi-convex likelihood ratio. So like I said, it pushes towards the G types being more spread out. And we're going to require that the length of the support for the good types is bigger than the length of the support for the bad types. We'll say an environment has more B spread if you have quasi-concave likelihood ratios and the length of the support for the B types is bigger than the length of the support for the G types. We don't think either of these two kind of restrictions are super important for our comparative statics. We're working on developing for others, but this is kind of going to be technically useful in our construction and kind of giving us a little bit more structure on the environment. Okay, last thing I'm going to do is that I'm going to want to talk about changes in the dispersion of the nuisance parameter. And to do that, it's useful to reparameterize the nuisance parameter in terms of quantiles. So we'll let QB and QG be the quantile of the realization of the nuisance parameter for a bad type and a good type, respectively. Okay? And then we're going to introduce these scaling functions, beta and gamma, that map those quantiles into the realized nuisance parameter. So beta of Q of B will be the nuisance parameter for the bad type at the quantile Q of B. Gamma will be the corresponding thing for the good type. Okay? So these are just kind of, pinned down exactly by the distribution for the CDF for the bad type and the CDF for the good type. Okay. Good. All right. Last definition, and then I'll get to the comparative static. We're going to say that an environment H has more informative equilibrium than an environment L if the set of equilibrium information structures about the scale type under H, weak set order dominates that under L in terms of Blackwell informativeness. That is, for each equilibrium environment H, we can find an equilibrium environment L that's Blackwell less informative, And for each equilibrium environment L, we can find an equilibrium environment H that's Blackwell more informative. So this is the kind of what you would want for making comparisons for these equilibria sets. Okay. All right, so our comparative static is we're going to fix an environment L, and we're going to look at changing the distribution of good or bad type preferences in some environment H. So what we show is that there exists an alpha greater than or equal to 1, such that for an environment H differing only in the distribution of the nuisance parameter for good types, if gamma prime of H is greater than alpha times gamma prime of L, then H has more informative equilibrium than L. If we change the distribution of bad types by basically by compressing the bad types, we're going to similarly get more informative equilibrium. So formally stated, we say there exists an alpha between 0 and 1, such that for an environment H differing only in the beta, if beta prime of H is less than alpha times beta prime of L, then H has more informative. Okay. So basically, this alpha is kind of saying that we have enough dispersion in the good or enough decrease compression in the bad types. Dispersion basically says that gamma prime of H is greater than gamma prime of L, or that compression would be that beta prime of H is less than beta prime of L. So in point 1, we're saying that as long as the good type is kind of more dispersed enough than under H than L, we get more informative equilibrium. Or if the bad type is less dispersed enough under H than L, we get more informative equilibrium. Good. What time did we start at? I think I'm running low on time, so.
Yeah, I think you count with 5 more minutes. Yes.
Okay, I'll wrap up pretty shortly here. So I'll just give kind of a rough sense of the idea, which is that we're going to basically, for each environment in L, what we're going to do is kind of construct an environment in H that has an equilibrium that's Blackwell more informative, and kind of similarly the reverse. Okay. So we'd like to have a kind of a useful way of comparing the informativeness of equilibrium. So we're going to do that again through these 5 functions. These are the pairings between good and bad types. Here we're kind of reparameterizing in terms of quantiles, and so it's going to look like this kind of convex function here. This is convex because reputations are increasing as you increase M. So you can show that this is that generates convexity. Good. And so the task is basically if we kind of have these equilibrium pairings, how can we say whether one is more informative than the other? Okay. So to do that, we're basically going to rely on this result from a Jewett note in 2007 that we found very useful, which says that what you can show is that basically if the pairing phi prime of H is everywhere lower than the pairing phi prime of L, or phi of L, then the equilibrium under H is Blackwell more informative than the equilibrium under L. So all we have to do is show that we can rank these 2 pairings in the following way. And if we can construct that, then we're done. Then we have a Blackwell comparison. Okay. So let's just suppose that let's think about the environment where we're going to have a more dispersed good type preference. We're going to increase the dispersion of good type preferences relative to bad type preferences. And what we want to do is basically construct a new equilibrium pairing that's going to be everywhere lower than our previous equilibrium pairing. Okay. Now the proof is quite complicated because it's constructive. We have to deal with pooling and existence issues. So I'm not really going to go into the details here. I'm just going to provide one kind of high level detail, and then I'll wrap up. So let's define eta of L to be basically the marginal material payoff from changing delta for a bad type with a kind of the nuisance type QB. Okay. Then let's kind of consider an equilibrium pairing phi under L and think about what's the local IC condition for that type choosing to mimic a type slightly higher than themselves. Well, the first order condition basically just pins down the reputation as equaling the change in the marginal material payoff. So you have to look at how much does the marginal material pay as I increase delta, and then how much does delta increase as I mimic a slightly higher type. Okay. So what we can show is that if you focus on this second term, notice that it depends on the gamma prime here, and phi prime and beta prime. If I increase the phi prime holding fixed, beta prime and phi prime, that's going to increase this change in delta, which basically is saying that if I were to hold fixed the equilibrium pairing, that mimicking a higher quantile under H now requires more movement along the frontier. It requires me to choose a much larger M if I want to mimic a slightly higher type. But that's costly for me. And so what that now pushes me to do is to choose lower M. But these lower M are exactly the M at which it's easier to have skill-based differentiation because we have this delta prime is larger. That the types, the difference in types marginal material payoff is more driven by the theta term relative to the nuisance parameter. Okay, so I apologize for going over time. What have we done? I'll just wrap up here. What have we done? We've studied a general model of signaling with plausible deniability. Tried to study kind of a general setting where we kind of tried to limit the assumptions we place on actions, our types, and payoffs. We've characterized the equilibrium set, show that it takes a kind of a nice, quite tractable structure. And we've explored these in comparative statics on the informativeness of equilibrium, understanding how the spread in G types preferences or B types preferences impacts that informativeness. The tools we develop here are also kind of useful for studying comparative statics in other dimensions. Think about increasing the cost of taking various actions for both types or increasing the reputation concerns. We can use that to develop very similar comparative statics. And then I didn't talk about it today, but we can apply this to a lot of kind of interesting examples and think about design questions. But yeah, thanks everyone, and look forward to hearing your thoughts in the discussion.
So thank you very much, Andrew. So we're gonna open now the questions, the Q&A part of the talk. So I'm going to start with the panelists, just following alphabetic order. So Ian, do you want to start with any question or comment that you may have?
Sure. I guess one thing that I was a bit curious about, we had this discussion about how rho had to be high enough, and that sort of got me thinking about how does the set of equilibria change with rho? I guess this is more in the spirit of maybe the Franklin-Kartik modeling information paper, but I wondered in your setting if you can say anything about that.
Absolutely. Yeah, we have a nice clean comparative static for that, which is that if you increase rho, as long as we're in the kind of the range that we're talking about, equilibrium informativeness goes down. So similar idea to Franco-Kartik, and you had the same comparative static in your paper, but it's very natural. So if you place more weight on reputation concerns, it's harder to distinguish people because everyone's going to want to pool with the good types, and we're all going to kind of compress the actions that they choose. It's kind of interesting, actually. It's not necessarily the case that as you take rho going to infinity that you end up with pooling on one action. You can actually have non-degenerate spans of actions being chosen. It's just going to be that along that span, the reputation converges to being close to the prior.
And maybe following up, the set of actions that are taken, does that shrink monotonically with rho or not necessarily? Because I know it came up that informativeness and sort of the range of X don't necessarily map one-to-one.
The range of actions being chosen, I mean, there exists multiple equilibriums, so that range is there's a non-degenerate. I don't have like a weak set order comparison or something like that for that. We could think about that, but I mean, my intuition would be that it it kind of naturally compresses, and doesn't have to go to degenerate as well. We know. Yeah.
Thanks.
So, Roy, do you have any final question?
So I guess one question I had is when I'm trying to think about applications and like changing this case, generally how I would think about it is like you change the noise in the observation. So like I'm trying to do a test to screen students, and I can change how sort of adaptive the test is at the high levels versus the low, and I can't actually change the nuisance types. Do the broad results go through if I can sort of just change how like noisy the action is at high versus low types if you put enough structure, or is that just a completely different model?
I think it's different enough that I hesitate to place some conjectures. I think the types of I'll say something about kind of the types of comparative statics we might have in mind, for that type of design question, is thinking about something like, that, whether I give kind of people access to test prep. And you might think that kind of rich people can kind of pay tutors that are going to give them the access, and poor people can't. And so there's a lot of heterogeneity driven by wealth. And that if I kind of make test prep free for everybody, then that kind of compresses the kind of distribution of what kind of getting tutoring help can help with. And you might think that that also correlates with the skill types, kind of whether test prep is helpful for you at all. Maybe you're really smart, it doesn't matter, you were going to do great on the test anyway, or you're really dumb, maybe like just test prep doesn't help you, you're kind of overwhelmed. So you could think about kind of changing that differentially. We could also then think about kind of maybe comparisons of changing the information that the observer has about your type. So if I kind of make wealth observable, that might kind of shrink the distribution of kind of underlying uncertainty about the nuisance parameter, and perhaps differentially for types as well, depending on how wealth and skill interact in kind of that nuisance parameter. But yeah, that's the kind of the settings that I think kind of most naturally map into our framework. Yeah, good question.
Thank you. So any other question from the audience?
I have a simple one in a way, which is you mentioned some distributions satisfy these quasi-convex orders. I mean, these are difficult things to get around your head too. I mean, so for example, for the normal, is it just about the variance, or does the mean also matter? Do we have a closed form definition, something like that?
Yeah. So for a normal, all that matters is the variance.
Okay.
If you have higher variance for the good types, you get quasi-convex. If you have higher variance for the bad types, you get quasi-concave.
Which is interesting because they might have very different means, and therefore, yeah. Okay.
Yeah.
So I guess for the beta, then it does matter what the mean is, I suppose.
Yeah, I think it does. For the exponential, you actually have monotonic likelihood ratios, so it's both quasi-concave and quasi-convex.
Okay.
But yeah.
Okay.
Yeah, I apologize. I know it's a bit fast, the quasi-convex.
No, fine.
Because we have to introduce it, but it's not.
I mean, it's a characterization, so you're using whatever is equal to necessary and sufficient. I was just more worried about sufficient conditions. So let's put it that way. Yeah.
So Andrew, I have a question. It's just like a wrap-up question. No, I mean, probably you mentioned at the very beginning, no, but after the talk, no, and then the intensity of the formalization that you have provided us, I mean, I probably forgot. So, I mean, to me, I mean, if I go look backwards to your talk, I mean, what caught my attention the most is the richness of the action space. So is that really the main, the main technical contribution of your work?
I think I think there's some contribution there. I think the comparative statics are the main contribution. I think that's actually the most difficult part is deriving the comparative statics.
So I mean, even in the case of a unidimensional action space, the comparative statics are not, were not known.
For this case, no. So there's some Alex and Naveen in their paper on muddled information, they have a lot of comparative statics on rho, for kind of some general cases. And then they kind of focus on a particular elliptical distribution that gets you a lot of tractability because you can solve things in close to closed form, I think. And they have some comparative statics, but no one's done the kind of, I think what we view as kind of the main contribution for our comparative statics is really the doing changes in the dispersion for good versus bad types differentially. Okay. And then the tools we can use, we can do other kind of comparative statics like this rho that I was talking about that Alex and Naveen do as well, and Ian has in his paper as well. So that's kind of how I would summarize it. So.
I see. And just as a final question, on the title, why plausible deniability? Isn't that, something typical of any signaling model, or am I missing something?
Yeah, so I should have emphasized where we're calling plausible deniability is that when you have good types with lots of preferences, when good types take multiple actions, that gives plausible deniability to these actions. So if I see you take a low action, if I knew for sure that was a bad type, no one's going to take it. But if there's some good types that want to take it, maybe you're still going to have a bad inference, but it's not going to be catastrophic because there's still a little bit of uncertainty. And so really what that's allowing is bad types to sort without kind of fully losing their reputation. If you have one good type, then they're going to choose one action and you can't have any kind of plausible deniability. So yeah, that's where we're going with it. But other suggestions are more than welcome if people have.
Well, it's a nice title. Okay, so thank you very much. Probably it's time we finished the official part of the seminar, and we thank the speaker Andrew and the panelists Roy and Ian for being today with us. And well, we hope to see you next week. For those that want to remain for informal talk, we're gonna stay for a few more minutes. Okay, so thank you.
Yeah, thanks.